Looks like we're just about there, folks. Welcome back, everyone. Almost there. Well, it's official. Looks like we can get started. Welcome back, everyone. It's week 15. That's pretty much where everyone wants to be when you start out a semester in trigonometry. So what we're doing to this week is finishing off section 8.3. This is going to be the last section for the entire course. And so that means this will be the last section that can appear on the final exam. I can't collect homework on this since there's no opportunity to really grade and have them collected on the final exam week. So instead, I posted these suggested exercises. This would be the list of exercises that will help you learn the section well. And when I go to write the final exam, I'm going to ensure that I write a problem that's similar to the stuff you're doing here, similar to the things that we're doing in the notes, so that we're not doing anything too wild. I do understand that's the last section of the course, and so I don't want to go too far off the rails. Expect exactly one problem, maybe two parts potentially. But let's finish that one off, and after we do, we're just going to immediately return to the review, not return to, but begin the review document here. This is a selection of questions over the whole course that I feel like is good representative questions for an actual honest final exam. Well, aside from that, also keep in mind when you're reviewing for the final exam, every one of our exams has a formula sheet on the last page, and no difference on this one. This is the real last page on your actual final exam. Let's take a look at it now that we're here. So the first thing you'll notice on the first page of the last page of your final exam is you'll have the sum difference identities, double angle identities, reduction formula. This is essentially the same handout you got on exam 2. Then on the next page, there's going to be some plotting, so I felt like this handout from exam 1 is going to be really helpful. And this as well for dealing with inverse functions, which are always tricky. So both pages will be provided. You can tear it off just like before. And that means when you're studying for the final exam, pay special attention to this page, not just what's on it, but what's not on it. You'll have to memorize the unit circle, where your angles are, that kind of thing, your reference angles and the outputs for sine and cosine, and other things like your Pythagorean identities, knowing that secant is 1 over cosine, tangent is sine over cosine, those kinds of things are what we have to memorize for the purpose of the final. Any questions, folks, so far with the announcements? Okay, and like we discussed before, our final exam is kind of strange. We have 2 classes, and for us, our final exam is officially held at this time if you are in the in-person section. It's a week away from today, from 8 p.m. to 10 p.m., but I'll still put out that feeler, or not feeler, but a reminder to folks. If this is a horrible time for you, then I totally agree. It's rough to do those late exams. On the same exact day, in the same exact classroom, I'm giving another exam from 5:30 to 7:30, which if it's more manageable for you, just send me an email or discuss it with me after class. You're welcome to just join the 5:30 exam. So if that's a better time for you, then I'd rather you do your exam at a better time. There is a danger in that, though. You have to make sure I hand you the actual exam that goes with the course. It's easy for me to mix that up when there's 2 sets of people in one room. Well, any questions, folks, about that exam? Oh, we've got a chat. Kiana asks, is there an answer sheet for the practice exam to check our work with? Yes, there's going to be an answer sheet. I don't think I have it published just yet, but I intend to. Correct me if I'm wrong. I think you're referring to probably this one right here, right? So I do intend to post the solutions to this document here. And aside from the other things, let's see, I forget what these all are, even though I published them just this morning. The sample exam version 2, this one, let me double check. Sample exam problems version 2. So if you go to version 2, what you'll notice after you stare at it long enough, this is the whole course that we went through. These are the same exact problems that we ran through when we were doing trigonometry. So there's a lot of stuff on here. And if you're looking for the solutions, what you would do is go to the corresponding section 7.3 up here in Moodle, and you'd have the answers to those questions provided in this location. It's a long document because version 2 is the entire class. It's your lecture notes with all your formulas reduced or removed, so it's just the problems. That makes it a little bit of a challenge to solve them because now we have to solve them cold when you're looking at that. But version 2 sample exam problems, not necessarily meant for you to solve every single problem on this 16 pages. Again, that's a semester's worth of work. The real use of this is for targeted practice. You can look at, say, the sample exam here, or the other sample final exam problems to decide what section do we really need to take a closer look at. If you feel like maybe it's solving trigonometric equations, then go to this document, go to section 7.5, and you'll get some extra practice. This document right here is the same sample final exam problems that we've been looking at throughout the whole course, but it just now goes all the way down to section 8.3. So these are more questions out of the textbook, our free textbook. So if you feel like these are pretty supportive questions, this would be a good place to look. Yep, you betcha, Kiana.
So
I also want to post additional stuff, but sorry, go ahead, Hayes.
sorry. So that final exam spring 2021 was like 15 questions. Are we going to have like around 15 questions too?
Yeah, I'm going to go for about the same length. Absolutely.
So like 2 hours, like around there?
16. Yes, I'm going for, actually, I'm not really going for 2 hours. What I'm going for is an exam that's about an hour and a half in length. So that way you would have additional time to double check problems.
Yes. Okay, thank you.
Yeah, absolutely. Also, notice that a reminder is you would need a calculator for this exam. On the third exam, it was more just an extra thing that you could have, but you probably didn't use it a lot. You will require the calculator on this exam since there will be problems that ask you to give a decimal approximation. Typically, the chapter 8 kind of problems will be asking that. And again, I'll be posting more documents here. I want to post the blank exam 1, blank exam 2, blank exam 3 shortly, because those would be great things to take another look at as you're studying for the final exam. But other questions or comments, folks, so far? Okay, well, let's finish off our section 9.3. Then we'll move into this review document, and we'll be back there when we come back on Thursday's class, just doing more problems out of that section. However, I wanted to offer to the whole class, if there's a review question that you'd like us to do aside from what's here, this is just what I'll work on if we run out of questions. I'll be very happy to answer your questions first, whether they came from homework, old exams, or anywhere at all. Don't hesitate to start with those, and we'll be sure to hit those questions too.
Can I start with like the exam 3, like our last exam? I think that there's a number like, let me check. Exam 3, number 3, like the tangent ones, like the half equation ones?
Yeah, absolutely. When we get into that review, let's start off with that question. But we have to first finish off our section 8.3, and then we're going to move into the review right after.
Okay.
But yeah, I'll be very happy to take a look at that question with you. In fact, just to make sure I don't forget, let me write this down as well. Exam 3 and the one with tangent.
Like number 3, the one with tangent, like tangent alpha by 2.
Gotcha. We'll be sure to go after that one as well. Okay. Oh, we got another chat. Kiana asks, you said chapter 8 won't be on the exam. Oh no, chapter 8 is on the exam. Section 8.3 is the last one that's on the real exam. So it goes from section 5.1, the start of the course, and because it's comprehensive, our exam is going to end on section 8.3, this one right here. Other questions or comments so far? Okay, sorry for the confusion with that. I must have misspoke, but yes, chapter 8 is on the final exam. One thing I might have said that could have caused a confusion is when I go to write the final exam, one thing that does happen is section 8.1, 8.2, and 8.3, it wasn't on exam 3. But that doesn't mean I'm going to give extra emphasis on those. Expect at most one question per section is what I'm really going to be going for. So I won't be throwing additional questions just because it wasn't on those exams. But any last questions or comments so far, folks? Okay, well, let's get started. We left off in section 8.3, looking into polar coordinates, but that's a whole new coordinate system that we took a look at before a weekend. So maybe let's review example 1 just to see what are we doing in this new setting. If you see something indicated as polar coordinates, I'll often start by writing r theta, just as a reminder, you're not dealing with your ordinary Cartesian coordinates. R is going to be a directed distance away from the pole, and theta is going to be an amount that you have to rotate by. So this portion right here is the polar axis. Any angle at this location is going to be measured in standard position off this polar axis. So if we're plotting 5 7 pi over 4, what we do is we rotate until we get to 7 pi over 4. Here it is. And if it's a positive 5, we just count 5 tick marks down, and we end up right here. At distance 5 down at the angle measurement, 7 pi over 4. Might as well put that 5 there. So that's the punchline to polar coordinates. Any questions about it so far? Okay, so if you can plot polar coordinates like these, and we'll do some more on these notes, you're in good shape already. I'm not going to ask anything too spectacular or too crazy on the real final exam. There'll be common questions like you're seeing here. The other thing we did was we took a look at the polar axis, this one, and the Cartesian plane all at the same time. We showed how to do some conversions. These two equations convert from polar coordinates into rectangular coordinates, and they are nice equations. All you have to do is give the value of r, take cosine theta, multiply them. That's what we did right here. The x-coordinate was found by taking this 5 and multiplying it against cosine 7 pi over 4. Cosine only because it's the x-coordinate. Likewise, for the y-coordinate, we indicate it as y. We would take 5 and sine of the same angle, sine because it's the second coordinate, and putting them all together, this is the coordinate of that point, which is in polar coordinates, down here in Cartesian coordinates. We're going to do it all over again, but now going in reverse from Cartesian or rectangular coordinates now into polar. But any questions, folks, or comments on that first example? Exactly. It would be a circle of radius 5, which is a great way to think about it. In fact, when you look at polar graphing paper, it kind of goes like this. I lied. Let me try again. It kind of goes like this. You'll have a circle here at a certain radius, a new concentric circle at another radius, and over and over and over. That's what a polar coordinate system would look like if we were doing it on, say, like graphing paper for polar coordinates. That's really, really hard to draw. So when you're doing it in practice, people just typically draw the polar axis and this one ray. But that's absolutely right. We're really just looking at a whole bunch of circles, all centered at the pole. Well, let's try this again now from the reverse point of view. These are in Cartesian coordinates, and we would like to convert them to polar. Really, this is a good opportunity to review a good amount of just trigonometry just on this spot. So we'll approach this problem as essentially a final exam review question. There's a lot more going there than it seems like. I'd say a first good idea, though, if you're doing a conversion, let's plot first the point in the rectangular coordinate system. -1, 3 would go here in quadrant 2. So it's right there. But at the same time, there's also a polar axis. I'll draw it this way with this lighter shade of blue. And we want to find the polar coordinates of that point, which is at -1, 3 in rectangular coordinates, which means we need two things. One thing we need is an angle measurement going this way. So some value for theta. And the second thing we need is the length of that segment, and that's going to be r. If we can find both of those, we will have r theta. So that's the setup so far. I'd say the easiest thing to do is solve for r here. This one's not too bad. Let's use a special color maybe. The formula for that value of r is simply r squared equals x squared plus y squared, and that's nothing but Pythagorean's theorem, really. So it's a nice formula in the sense that you do have your x right here. R squared is now equal to -1 squared plus 3 squared. And some folks have mentioned you could just take the square root right here. That's not a bad idea to take if you prefer. I usually leave my r squared in this position and just crank it out. as we see here. This is now a positive 1 plus 9. So r squared is 10, which means r, if you take the square root, you get two potential values, positive or negative square root of 10. That seems weird, right? Ordinarily, if you indicate r this way, you're thinking of the positive root. But it is actually to our advantage to consider both roots as potential solutions to this problem. A tangent, you got a complex value? Well, your tangent should give you a real value, because when you go to take tangent on this problem, well, that's what we're about to do. We're going to actually solve a trigonometric equation, but we should be getting a real number out of that. But let's take a look. After getting this, we'll come back to this confusion. To get your angle theta, the second equation is this one. Tangent theta equals y divided by x. Same equations at the very top when we were looking at those conversions. Our y value is 3, our x value is -1. So now this turns into tangent theta is -3 altogether. It's just 3 divided by -1. But that's a trigonometric equation, so this takes us to section 7.5. Also at the same time, calculators are on the table. It's a 7.5 question that also uses one of these things. Let me minimize that. Sorry, I should have minimized that at the start of class. There we go. So we'll show how to use the calculator to solve this equation at the same time. First thing you do is just take tangent inverse of both sides. So I usually write it out this way. You don't have to copy this step. This is more for the sake of the notes to connect the dots with other concepts. It goes tangent inverse of tangent theta equals tangent inverse of -3. This is really section 6.3 now. This is the major punchline of inverse functions, that this tangent is canceled with its inverse. We get down to this line, theta equals tangent inverse -3. As folks have mentioned in the past, though, that can be a confusing step. If it's confusing to you and you'd rather see it this way, that's absolutely okay. I put this middle line in just to connect the dots in the inverse function section. Now, there's not much more to do but punch this into a calculator. I'm going to use degree mode in my calculator when I do this. And here's what it would look like. Once I get that going. Okay, first, hit that button until you see degree mode. It should say deg for degree down below. After you hit that button, the next thing you need to hit are the keys second and the tangent. That's what will produce tangent inverse. I think it prints it like that. Punch in -3 and close the parentheses, and you should be getting an angle. Confusingly, though, that should be a negative angle. I don't have a real calculator at the moment. Anyone happen to have that angle?
71565051118.
Awesome. I lost a few digits, but how about there? Let's go with -71.565. Yeah, you can do these in radian if you prefer. Totally up to you. I feel like this problem is a little bit easier to visualize in degree mode, so I kept it this way. Sorry, say again? Oh, sorry, I misunderstood what you said earlier. I thought you were saying complex valued or imaginary. But yeah, it's going to be an irrational value for these kind of problems for sure. So yeah, good call. These are irrational, which means we had to absolutely use the calculator to find that angle. Keep in mind, calculators are required on the final exam. That's my standard reminder. But notice the other conflict. Sorry, say again? I gotcha. Well, here's the next issue with this angle. It says it's at -71.56 degrees, and let's look at where that places us. Not up here, it's way down here. This is the angle we actually found, -71.56 0.565 degrees. And you know what? That angle actually works to specify that point right here in polar coordinates, as weird as it sounds. Let's take a pause right here. Sorry, question first? So, yeah, this one is going clockwise in that direction. Oh, sorry about that. Yeah, it's kind of like a polar axis. This was at 0 degrees, but a new axis at negative 71 degrees is what the arrow is indicating. But to show what we're about to do on the next step, let's come back up here to this really weird concept. When we were plotting points in the polar coordinate system for the very first time, we made this remark. This point here at 3, pi over 3, so this one, puts you at this polar axis, pi over 3 tick marks up, but it's the same position as this one. You can go to the diametrically opposed direction for pi over 3. If you say a negative 3, it means on this branch, go a distance of negative 3. So you're going the other way. So if you have the wrong angle, just use the opposite sign for your directed distance, r. Directed distance reminds us it could be positive or negative, as weird as that is, and you're in the right shape. So keep this in your mental chalkboard. Come back down to our current problem. We found an angle that's diametrically opposed to the one we want. You can add, say, pi to this to end up right here. But I think the best answer, the most convenient answer rather, is this. We're going to use this rotation, negative 71.565 degrees, and we're going to use the negative distance, negative root 10. That means on this branch, we're going the other direction, landing here. And then for the angle, negative 71.565 degrees is in fact the right angle, the correct angle. I should say right angle. That sounds like 90 degrees. That's the correct angle. So that's a tricky problem, but any questions, folks, on the solution here? Okay, I would say this is probably the better way to solve it, but the reason it's so weird is right here, when you said you're using tangent inverse, it meant that there were some really big restrictions. You cannot get a positive pi over 2 or a negative pi over 2 as outputs, and you couldn't have even been in any one of those quadrants. So the calculator gave us that angle right here. It was inconvenient, but it matches up with this one. We just had to pick the negative sign whenever that occurs. Any questions, folks, with the solution here? Okay, well, all this stuff is important. I'd say really understanding polar coordinates, you really have to hit example 1, example 2 pretty hard to get a feel for how it goes. But I want to give a big hint on the final exam, because this is our last section. I realize it's a time crunch to study this. On a real final exam, I'm probably going to ask a question that looks just like this one. Different values right here for polar coordinates. So if you can get through this problem, you're in great shape for the final exam relative to this section. Before we launch into it, any questions at the moment? Okay. It says compute the distance between the given points that are in polar coordinates. And really the first thing you want to do before you compute those distances is plot the polar coordinates. Your ordinary distance formula doesn't work on this because they're not XY coordinates at all. There is not quite a new formula. It turns out there's an old formula that we're about to use. We just have to see it. That's going to be the first step, just plot the points. The old formula that we're going to use is just law of cosines. So this problem is a big review on the final exam. It's section 8.2 and 8.3 all at once. You could, but if you look up here, that's a process, and it's actually a pretty difficult process for just random points. So although you could convert both points into rectangular, it could take, oh, hang on, let me think about that. These were points in the rectangular coordinates form. But for given polar coordinates, no, you're absolutely right, Michael. The conversion is not hard going in this direction. from polar to rectangular, you would have to do these two computations, then you'll get 2 points. Then you'd use the distance formula on those 2 points, and that would be a good approach. I would say, in all honesty, that's a competitive method. It might be just as fast. Other questions about this so far? Okay, I would still say the polar coordinate method, just staying in polar coordinates, could be a little bit faster, but let's give it a try and make that determination after we complete the problem. My first step is just to plot them. So here's the polar axis. Starts with the pole, the origin here, goes to the right horizontally. Let's plot this point to start. So it's at an angle of 11 pi over 6. 11 pi over 6 is just 30 degrees away from a full rotation. That doesn't look quite right. It doesn't have to be perfect, but let me try to do a little bit better. So here's 11 pi over 6 on this one. And it says go a distance of 2 in that direction. So 1, 2. So we got it. That's our first point. Then just do that all over again with this angle. Pi over 4. Well, first, this way is pi over 4. That's 3 pi over 4. So that way would be 5 pi over 4. So it goes about like this. We have to go a distance 3 down that segment. So here's 1, 2, 3. And that point lands in that location. Yeah, go ahead.
You're going 2 or 3, like, is it just kind of where it would perpendicularly intersect from, like, say, your x-axis when you're trying to find those increments?
It's more just along this particular line. What do you mean by perpendicularly intersect, just to be sure?
So, like, to make sure, like, your spacing's right,
Yeah,
would your, like, 3 more or less be perpendicular to, like, -3 on the x-axis?
oh, it wouldn't necessarily. Yeah, -3 on the x-axis could be about 1, 2, 3, and they don't necessarily have to overlap. Let me see if I can fix the scale on there to make that more believable. So I want to keep that equal scale. So here to here is about the first tick mark. Same scale here to here. Same scale here to here. I see what you're saying now. When this projects up, it would be at a different value.
Okay.
But what it is a huge circle that kind of goes like this is where it's really connecting through.
So, like, the radius.
Yeah, so it connects through 3 here, but if you project perpendicularly up, it's not guaranteed to be a 3 any longer, unfortunately.
Okay.
Yeah, so it's more about the radii, the radiuses.
Okay.
Other questions so far? Okay, well, we've got 2 polar points. What we wanted, though, is the distance between them. Let's plot that next. It would be from here to here, and that's the distance d. So this is now really just law of cosines. Law of cosines is going to give you an interior angle, theta, that we have to work on. From here to here, we need a side length, but we know that side length. That's 3 coming from this coordinate. Next, from here to here, we need another side length, but it's 2, just like from before. So we're just finding the actual distance here in a non-right triangle, whatever that angle theta is going to be. So law of cosines says the following. This thing, the thing we want to calculate, d squared, is going to be a squared plus b squared. It looks like Pythagorean's theorem there, but that's not necessarily 90 degrees. It's definitely not in this problem. So we go minus 2ab cosine of theta. So now we just need to plug in information. The distance is the unknown, so still distance squared there. But for a squared, I'll think of the a as the value 2. So that'll turn into a 2 squared. For b squared, we're looking at this distance here. And you know what? It wouldn't hurt me to just call this a. I think that makes it a little bit more readable. That's the a and that's the b. Anything additional you could put on the problem that helps, well worth doing. It just takes a second. So we have to square the 3. then minus 2 times both of those values, 2 times 3 for A and B. And then cosine of the angle theta. I'd say this is the most confusing part right here on getting that value. That sounds about right, exactly. All you have to do is take this angle and subtract pi over 4. And actually, you can subtract in any order, it turns out. If you take 5 pi over 4 minus 11 pi over 6, you will get the same thing as 11 pi over 6 minus our 5 pi over 4. Not necessarily, because the good news is, sure, if you subtract differently, you're going to get a negative sign, but cosine is forgiving with that. Cosine of negative theta is cosine theta by the opposite angle identity. But what that tells us is it's irrelevant how you subtract. Your negative sign is just going to fall off either way. So that's kind of nice in this certain sense. So I'll say here, this is the most confusing bit, but all you have to do is just pick one angle, pick the other angle, and, well, it would have been nice if it was a 6, that's over a 4, and then just subtract in that way. Now we need a least common denominator, so that would be 12. Multiply this one by 2 over 2. 22 pi 12ths. Multiply this one by 3 over 3. That's negative 15 pi 12ths. And I'm getting a 7 pi over 12 altogether on this one. If you subtract it in the opposite way, it's negative 7 pi over 12. But from that identity, it's irrelevant. You'll get the same exact value. So 7 pi 12ths comes down right here. And at this stage, we're basically done with this problem. This is going to be a rounding problem on the real final exam. So once you get to this stage, just jam it all into your calculator and you're in good shape. But notice though, I put 7 pi over 12 here, so there's a real danger in your calculator. If you use this, be sure to use radian mode. It's really just heartbreaking, I'd say, on a final exam to do everything right, even put it in your calculator right, but your calculator was in the wrong mode and your answer doesn't make sense. But on a real final exam, if I saw this, I'm probably going to give you almost every single bit of credit. And if you made a mistake on your calculator, I'm a little bit less worried about that. So show me a paper trail, that's where I award the partial credit, and you would be less worried about any simple mistakes. So let me see if I can calculate it along with you. In the context of polar coordinates, yes, your distance r could be a negative directed distance. In this case, though, it should only be positive. Oh, gotcha. Yeah, in this context, this distance was meant to be just purely positive. Yeah. So let me see if I can get this in. First thing I have to do in this calculator, however, is go down to, yeah, I'm in the right mode. We're using radians on this one. And it'll be then 2 squared. Oh, good question. I think it's that button right there.
Oh, okay.
It flips it between the two modes, radian and degree.
Degree, radian, and GRD.
I'm not too sure. Gradient, that might be something like gradient of the road, like a percent slope. I'm honestly not sure on that one. I'm good with gradient or radians and degrees, so those would be the two we'll work on. Other questions so far? Okay, thanks for asking about that. I mean, for using calculators, this is the new mathematical thing we have to be very careful about, radian mode and such. So down here, I'm going to put in 2 squared plus 3 squared minus 2 times 2 times 3 times cosine 7 pi over 12. And just to observe, there's actually nothing to memorize here. You can subtract in either order. Notice if I put a negative, this quantity will not change. That's awesome. I love even functions because it just wipes out that negative sign. So we get almost 16, which means the distance is almost 4. It's not exactly 4 though. So let's put in the distance squared equals 16 point, that's the wrong calculator, 1058. So last step, just take the square root of that prior answer. The distance between those 2 points in polar coordinates goes square root 16.10582. And let's see, we're rounding to 1 decimal place. Looks like a 4.0. It's not exactly 4, but it's awfully close. But we did it, folks. There's going to be a question really similar to this one on the final exam. I think it's got a 2-part question. I will ask you to first plot the points in polar coordinates, and then the second part, just use the law of cosines to calculate the distance. Like Michael was mentioning though, if you're just calculating the distance and you converted these to Cartesian coordinates and then use the ordinary distance formula in the plane, that's a good approach as well. And you can't be punished for knowing stuff. So if you took that approach, you would also get full credit in that way as well. But any other questions, folks, with the conclusion here?
Where did you get the negative for the negative 7 pi over 12 again?
Oh, gotcha. That's if you went in this route. So I subtracted 11 pi over 6 minus 5 pi over 4, but you might have went this way. 5 pi over 4 minus 11 pi over 6. If you went in that direction, you'd still get to this work of combining or finding least common denominator, but it would turn into 15 pi over 12 minus 22 pi over 12 equals the negative 7 pi 12ths. So this answer works just as good as this answer in cosine because of cosine being negative right here. So the major comment was, whatever angle you produce, don't be worried if it comes out positive or negative, totally irrelevant to the law of cosines. Does that make sense with that question there?
Yeah, that makes sense. Thank you.
Yeah, absolutely. Other questions or comments at the moment? A little bit more highlighting can't hurt. Let's put some on there. Well, congratulations, folks. I think we've done a lot of hard work ever since the first week of the class. This is where all the content would end for the final exam. And consider this pretty much what your real final exam question is going to look like. I'm just going to change the points and the angles that you see here, and it'll be the same kind of process. So now we're at the exciting end of the work where we're moving over to the review. This is also up there in the blank lecture notes if you want just blank documents as PDFs or Word documents. And we'll be uploading our solutions as we go through those notes. First, let me find them. They're right here in the review. That's way small. Let me zoom in on that. And I made this the very first question of the day because I feel like this is a tricky question to get through on a real final exam. After that, I have some equation solving, and you could think of this as a pretty representative sample of questions for a real final. It's going to end on some triangles that we see here using the law of sines, law of cosines. And so these will be our review problems for the last part of the course. If you have any questions when we come back on Thursday that you definitely want to see solved first on this document, please make sure to let me know. There's no reason we can't go out of order on these. But let's start from the beginning. They tell us tangent t is -3, and that the angle t is constrained between 3 pi over 2 and 2 pi, and we want to find the remaining 5 trigonometric functions of t. So this is a fun question in the sense that you kind of want to organize and start with the answer. We want to find sine of t. We're just going to leave these blank until we get there. Cosine of t. Tangent of t. This is the one we know, so -3 goes there. We don't have to solve for t, no. And we want to find the exact values on these. I think on the real exam, if I have a question like this one, it'll say down below, find the exact, well, that was weird, exact values. So I have that written in some problems on the final exam just to indicate we're going for those exact values. So then next, sine is corresponds to cosecant of t. Cosine corresponds to secant of t. And cotangent of t, we do know this value by visual inspection. Anyone see what that quantity ought to equal? Exactly. Just take the reciprocal of whatever is here. So -1/3 or 1/-3. So that's kind of nice. We are, well, 4 more to go, really. To get those remaining 4, you have options, and I'll leave it up to the class which way you'd like to pursue. You can use, well, we have information on tangent, so you might use tangent squared of t plus 1 equals secant squared of t, or you might use the right triangle trigonometry approach. Completely up to you on this kind of problem. Anyone have one strong preference over the other? Pythagorean's identity or right triangles? Let's give Pythagoreans a try. So if we go with the Pythagorean route, you might write tangent t is going to be equal to the opposite over the adjacent. We have a value of -3/1. So we'll form a triangle with opposite side. It'll be really a +3. And adjacent side will be a +1. So it'll look like about this. Let me try again. Want to make it a little bit steeper. About like this. Here's the angle T, and maybe what I should have done as a first step if we're doing the right triangle approach. So let me try again. Yeah. Mm.
Could it be any fraction that equals -3?
Yeah, so I think I see what you're saying. This tangent that comes out as -3 is also sine t divided by cosine t. So we need a value here, so that when we reduce the fraction, you get a -3 and gives us the right value for sine. Is that what you're referring to? There's going to be infinitely many different such fractions. So that is a real worry. There's exactly one, and that's a weird part. There's exactly one solution because there's constraints. This is one constraint right here. And the second constraint comes down from here, the right triangle. So even though there's infinitely ways to multiply two numbers, a number and its reciprocal to result in -3, there's exactly one way to get the sine and the cosine that gives -3 here and t in that right quadrant. So that's one thing that's kind of remarkable about this. And it's also the reason why we have to work really hard. We can't just take -3 and say it goes there. I mean, that's automatically wrong, right? Sine can never hit a height of -3, or that's a depth rather. It can only go as minimum to -1. So that indicates there is some weird work we have to do to get through this one. The Pythagorean theorem approach will give you a unique solution for secant, and SOHCAHTOA will also give us a unique solution for all of the other functions. But other questions at the moment? Okay, so there's definitely a uniqueness question going on, but my claim is this answer is unique. Let me know if I fail to convince you. So we have tangent t is going to be the opposite. I'll put a value 3 here. Some people put -3, and I don't think it's a bad approach. It just looks weird because that's supposed to be a positive length. Exactly. So I'm going to put a 3 there. 1 down below. That's going to be the adjacent side to t. But now I'm still not done. We need to find c, the side for the hypotenuse, but that's just now Pythagorean's theorem. C squared equals 3 squared plus 1 squared. Continue through this. This feels like a 9 plus a 1, so C squared is a 10. We take the square root. There are two answers, but we're taking the positive root in this context. So just a positive root 10. So now we've got a positive root 10 over here. We can start really just calculating everything. So for example, on sine t, on SOHCAHTOA, sine is going to be the opposite end. That's this. Divide by the adjacent end, root 10. Observe, I'm going to give it a little bit of space, 3 over root 10, because we also know our angle terminates in quadrant 4. In that quadrant, let's draw this out just to be specific. Here's 3 pi over 2, and here's 2 pi. Our angle t is somewhere out here, and I can guarantee you, though, sine is negative in that quadrant. So we get a negative value. But the moment you found sine, you also found cosecant. Just flip it, just like tangent to cotangent. So negative root 10 over 3 as well. And now it boils down to cosine. That means we are on the CAH part of SOHCAHTOA. Cosine of the angle t is going to be the adjacent side 1, divide by the hypotenuse root 10. 1 over root 10. And so now we can double check this. If sine is negative 3/10, negative 3 over root 10, and cosine is this value, you multiply by its reciprocal, these cancel off, and we do get negative 3. But there were infinitely many ways to make that cancellation happen, but only one way that's consistent with the right triangle and SOHCAHTOA, our definition of the trig functions on SOHCAHTOA, give us this as the only possibility. So let me eliminate this scratch so it doesn't get too foggy in there. Next, cosine t is 1 over root t. That means we know secant immediately. Just a root of t. We gave cosine and secant positive values because in this quadrant, we get positive values right here that we're working on. Well, this would be the approach through SOHCAHTOA, but maybe just because we have a couple more minutes and there's still a uniqueness question, suppose you did it this way, Pythagorean's theorem approach. Honestly, that's kind of my favorite approach. I think it's actually a little bit faster, but, well, no, I take that back. It is a little bit slower because you use multiple Pythagorean theorems potentially. So this organized a bunch of information. But if you took this approach, you would square negative 3, add 1 to get secant squared. This is now 9 plus 1 for 10 equals secant squared of t. From here, what would we do? We would just take the square root of both sides after getting a little bit of additional space. There are two potential answers when you take the root, but secant is 1 over cosine, and that means we have to have a positive answer. We're in that quadrant. So root 10 is equal to secant of t, but notice that is exactly what we produced right there. So there's a unique value for secant just using this Pythagorean identity, which then gives you cosine, and then you would have to use sine squared of t plus cosine squared of t equals 1, and that equation will give you sine at the same exact value. But that's quite a lot of stuff for one problem. Let me organize the notes by saying this is method 1. There's more work to do on method 1. And this one is method 2. It's a complete method because in a nice way, this right triangle conveyed everything you need to know about all 6 trigonometric functions, whereas method 1 just gives you secant and cosine. You need another Pythagorean identity right after. Well, any questions at all, folks, about running through this problem? Okay. I feel like this is a good one to get out of the way, first of all, because it is a tricky one, but it's also a pretty good review question in the sense that we did a lot of stuff. You have to know the relationship between cosine and secant. You either need to use the Pythagorean identities or Pythagorean's theorem in right triangle trigonometry. So this one question is reviewing like 25% of the class. It's kind of nice. When we come back, we'll hit the trigonometric equations. feel like these are always a little bit tricky, so I'll hit them a little bit harder. But if you have other questions you'd like to take a look at, please feel free to bring them to class and I'll be happy to work on them with you. But any last questions, folks, before we call it a night? Okay, that's all I have for you then. I'll see you all in Thursday's class. And we're just about there, folks.
Thank you.
Thanks, folks. Not running away, I promise. Here you go.
You're good. I usually don't just get up and run back there.